We started talking about special right triangles in class, but today in this video I'm going to talk to you about the shortcuts involved in the 30, 60, 90, and 45, 45, 90 triangles. First we'll discuss why which two triangles we call the special right triangles, why they're special, the relationships between the sides, which is going to give us our shortcut. I'll do the easy examples, I'll go through my preferred way of doing the harder examples, and give you a backup plan, and we'll summarize. There are two special right triangles. One is called the 30, 60, 90, and it comes from splitting an equilateral triangle in half by drawing an altitude from one of the angles to the opposite side. By doing that, because it's equilateral, the altitude is also the angle bisector, and it creates a perpendicular angle, so we get 30 degrees up at the top and 90 degrees at the bottom. The other special right triangle is the 45, 45, 90. It's also the isosceles right triangle, and it comes from taking a square and cutting it in half by drawing its diagonal in. These triangles are called special triangles because of the way they're formed, and the way that they're formed creates a relationship between the different sides. Like, for example, in the 30, 60, 90 triangle, this was the original side of the equilateral, so you could kind of imagine it's extending this way. So here's the altitude that was drawn in. If the original side length was 2, this side would be 1 because it was cut in half. Then we would already know 2 of the sides, and we could use the Pythagorean theorem to find the third. They're special because the way they're formed gives us at least 2 sides of the right triangle. Same thing happens with the 45, 45, 90. These 2 sides were the original side of the square, so they're both congruent to each other, which means we know 2 sides of the right triangle, and we could use Pythagorean theorem to solve for the third. As was kind of shown in the previous slide, there's a relationship between the side lengths that we can generalize. Usually you'll see, if you look it up, people will use the letter X. I'm going to say let's use the letter U, just so we don't get confused if there's an X in the problem that you're solving. This is the original side of the equilateral triangle, so let's call that 2U. It's nice to call that one 2U instead of just 1U, because that's the side that cuts in half to give you this side. So originally this side is also, let's say, 2U long, but when it gets cut, it becomes just 1U long on the bottom. Then by doing the Pythagorean theorem, let's call that H for height. We'll get U squared plus H squared equals 4U squared. And then when we take the square root of both sides, we'll get H equals, well, we can take the square root there, but we can't take the square root of 3. So we'll always get that relationship of U to root 3 for that height. And by the way, this side, which I will refer to as the long leg, is always across from the 60-degree angle. The U side is always across from the 30-degree angle, and the 2U is the hypotenuse. 45, 45, 90. Again, let's pick a different letter. Let's call it V. We have V squared plus V squared equals, we'll call it C. 2V squared equals C squared. When I take the square root of both sides, I can take the square root of V squared, but I can't take the square root of 2 without a decimal. This shows us that when we use the letter V to represent the sides, the hypotenuse would be V root 2. That means we can plug in anything we want for V, and then we would just get V root 2 for the hypotenuse. The easy examples follow the pattern, and it's really easy to plug numbers in. Let's take this 30, 60, 90 problem. This is across from the 30-degree angle, so this is the U. This is the hypotenuse, so it's 2U, and then that makes this U root 3. So C is 10 and B is 5 root 3. In this one, we're given the side across from the 60-degree angle, so that's the u root 3 side, which means that u is 4 and 2u is 8. Here we're given the hypotenuse, which is 2u, which means the u side is 10 across from 30 degrees, and that u root 3 would be 10 root 3. Here on this 45, 45, 90, we're given the leg lengths, which are, this one's 2, so this one will be 2 as well. This will be 2 root 2. Here we're given the v root 2 side, which means that v is 7, so our two legs are 7. Some of the examples are harder because we get a whole number where we think there should be a radical. What I like to do is take that whole number and set it equal to the radical expression. This side, the hypotenuse is 6, so I'm going to set that equal to v root 3. And I'm going to solve for v. I get 6 divided by root 3 is equal to v. And I need to rationalize this. That's why we practice that in class. I'm going to end up with 6 root 3 over 3, but we can cancel it out, and ultimately our answer is 2 root 3. One more example with a 30, 60, 90. This is across from the 60-degree side, so we would expect it to be the u root 3. Set that equal to 4. Solve for u. I'm going to rationalize it, and I'm going to get 4 root 3 over 3. That doesn't reduce any farther. That's going to be this side over here. And that would make this side twice as big. We only multiply the numerator, and I can show you that in class if you're confused about multiplying fractions. That makes the hypotenuse 8 root 3 over 3. Sorry that the video has gone on a little bit longer. Just wanted to point out that when all else fails, you can just use what you know about the triangle and plug it into the Pythagorean theorem. For example, we know that this side should be half of this side. So I could make this x and 2x. And I could do x squared plus 4 squared equals 2x squared. And then you could solve for x from there. Briefly, you should, in your summary, mention, if you can, summarize the relationship between the three sides and then what your backup plan should be.